Welcome, everyone, for another week's lecture of the Rising Tide Foundation Symposium on the Earth's next 100 years. We minimized it a little bit from the next 1,000 years, but I think that what we're going to be learning in the course of this presentation and many of our presentations will still have great application 1,000 years from now. So today we have the great honor and pleasure of once again listening to the thoughts and composition of Dr. Jonathan Tennenbaum. Dr. Tennenbaum's previous lecture on the stupidity of AI was just brilliant, and that's going to be a link in the description of this video for people who want to dig in a little bit more into some of the deeper epistemological concepts underlying some of the thoughts that are going to be shared today. The point of this current symposium, and the last couple of presentations tackled different positive, optimistic aspects of the Renaissance tradition in Africa, past and future. So what are the hopes and pathways that not only Africa, but all of humanity are looking at going into the coming century and beyond? Now, the question of the future obviously weighs heavily upon the present, since it is very underdetermined. There's a lot of potential for good and for evil. If we do have a society that is thriving in 100 years' time, which I have faith that this is possible and necessary, and so it must happen, there will be certain different standards of scientific and artistic and cultural norms and practice that will be understood, which today are very, I think, opaque. And I mean, people have had certain truths kept from them for certain unfortunate reasons. But all that to say, certain truths will be revealed, certain practices will be normalized, and certain bad patterns of habitual thinking about standard theory and other formulaic approaches to cosmology, atomic science, I think, are also going to be brushed aside. And so for that, I'm very, very happy that Dr. Tennenbaum has offered his time to share some of the thoughts that he's been working on for many, many years that touch upon this domain. So Jonathan, it is all yours.
Many thanks, Matt. And also this this event has given me, provided an occasion to once more think through some things, which is always useful. So we're about a little less than a century from the first codification of quantum mechanics, principally by Erwin Schrödinger and Werner Heisenberg. Almost, it was 1926, 1927. And I think that was, one can say that that was the last real revolutionary transformation of fundamental physics which has occurred up to now. I don't think it's the last one. I'm absolutely sure there are going to be more, an endless series of them. But what we've had in the course of the 20th century up until now is kind of elaboration, application of this, the consequences of this revolution, which has brought us a great deal of the technology and the scientific instruments and also approaches to science which we have today. I mean, electronics, semiconductors, chips, information technology, lasers, whole new generations of scientific instruments without which you would not have, molecular biology, present day chemistry in its present form, magnetic resonance, imaging, sensors, et cetera, et cetera, et cetera. Our whole understanding of physical chemistry what's transformed, of course, with chemistry is basically quantum chemistry, and so on and so forth. So also, of course, nuclear energy, as nuclear physics, nuclear energy, elementary particle physics, and so on. So this revolution at the time in the 20s, it started before that, but in particular, the 1926 kind of, what do you call it, a threshold or transition, raised a lot of philosophical and methodological, epistemological questions and problems and debates and controversies, which are continuing up to today. And for me, it's a very hopeful sign that there appears to be in the course of the last 10 years, 20 years, a revival of different sides of the debate, of which essentially one side more or less won out, which I'll go into a little bit. And now the debate is coming back, and is coming back not just as an abstract philosophical debate, but as but in connection with experiments, in connection with actual work on experimental physics, which then opens up the promise, additional degrees of freedom, laying the basis for a potential new revolution. So what are just to, let's say, to focus the broader or universal aspect, this quantum physics revolution brings up the very basic questions. I mean, in one way or another. One is the old question of the discrete and the continuous. For example, is a line a set of points? Or how many points do you have on a line? Well, can you even make a line out of points? Because points have no extension. So you can put a lot of points together, but you never get extension. Another question, do you have real jumps? Do you have discontinuities in nature? No, we have this saying, natura non facit saltos. Nature doesn't make jumps. But in at least the present way of thinking in quantum physics, you always talk about the quantum jumps. So this issue has come. Schrödinger, for example, one of the fathers of the creators of the quantum physics, did not believe that there are quantum jumps. And that's a whole other story. So it's still, in a sense, open. Then, of course, fundamental is the two approaches, the atomistic approach, the notion that matter is composed of some sort of more or less indivisible units, elementary particles, and the other direction, the notion that, and they're floating around essentially in a vacuum. And the other approach is that there's an ether, there's a continuous, some kind of a substance, which is the basis of existence, and the discrete objects are somehow thrown off as bubbles or whatever. They're somehow composed out of this continuum. So these issues, which are not, so to speak, factual issues in the usual sense, they're very much a question of the approach you want to take. And these are not the last words. There are other conceptions which could arise or could be developed, which would be ways out of the apparent paradoxes or dualities of these approaches. And that's very much to the point of where a new revolution might take place. So another thing is the clash which occurred in a very, very, I would say, violent in a certain way, in the context of the debate about the quantum physics, is the issue of different directions of philosophy, directions that are look for more universal principles and have the notion that the human mind can progressively understand, in some suitable sense, the world, and the other direction, more positivistic, that says, no, the human mind is limited. In fact, we can't say really anything about the real world. We can only devise words. We can give rules for manipulation. We can develop mathematical methods for predicting the numbers that we get from experiments, so-called operationalism. You define something as what you have to do to measure it, and your theory is some kind of mathematical apparatus which is supposed to predict what you do, what you get if you do this. If you do this, you get that, which has nothing to do with understanding anything. So they're very different sort of philosophical and methodological approaches which came into conflict in the 1920s. Already before that, of course, there's been a continuous kind of conflict going on since ancient times, but it took a very concrete form. So, of course, part of this is also the notion, the particular notion of science that came, is the idea you want to liberate yourself from metaphysics, which was associated with the church. You have the Enlightenment and so on. Well, I don't want to go into all of that. But a very important issue for me, fundamental in this, is really the question of intelligibility. What do we want from science? Do we want the basis to be able to make a lot of gadgets that work, or do we want more? Is physical science, physics, does it have a philosophical aspect, or a demand? Do we demand to, in some sense, arrive at an intelligible conception of the world, which is not simply an abstract conception, but includes the world of phenomena? Or is the human being, we're just plunged in this sort of chaotic mess and can only make correlations? So that's fundamental issues which actually came up because one side of this debate on the quantum mechanics took the position that the world is somehow intrinsically unintelligible, and you have to just, face the fact that we won't get any further, and we can elaborate, but we will not get further. There's some barrier, whether it's a barrier of the human mind or intrinsic barrier in the way the universe works. Okay, in this operational, I should just say, we'll get to it in the quote, the so-called operationalist approach basically regards conceptions as ways to bundle up sensations. It's a way to bundle data. It's just like a data classification. It's the name you put on a folder. That's a conception. And that you can't basically, in the last analysis, you never get beyond a pure mental construct. So, okay, let's now look at the debate, and I'm going to go into some specifics. In this debate, in the 1926, 1927, the famous Solvay conference, you basically had one group of physicists, particularly Niels Bohr, Heisenberg, Max Planck, and others, that took a very strict position, relatively well-defined position, in the direction I just indicated, that there's a barrier. You won't have an intelligible conception of the universe. For some reason, which they never really gave an argument for, they claimed this is somehow the way it is. Then another group, and that the quantum mechanics in a certain sense is, at least in some respects, the best you could do. It's and then you had people like Schrödinger himself, Einstein, who objected and said that the quantum mechanics is just a a partial theory, and you're not getting at the base level. It's leaving out something essential, and demanded an intelligible intelligibility. Let's put it that way. So let's go back. This was already going on before the advent of the quantum physics, long before it. And I'm going to focus on the so-called wave-particle paradox, and the notion of what is the nature of light, what's the nature of electrons, and so forth. I mean, you had on the one side, again, we get back to the discreteness versus continuity notion. On the continuity direction, concerning, for example, light, you had the wave theory of light, you had Christian Huygens. Later, the notion is that light is a continuous wave process. This then got, with the development of electrodynamics, the unification of magnetism, electricity, and the notion of a wave as a sort of a process of change in the magnetic and electrical fields. But a wave notion, a notion in which there's continuity. So, of course, there are a lot of questions here. You know, well, if light is vibrations of electromagnetic field, and for different frequencies you get different wavelengths of light, and you can unify radio waves and light and so forth. But what is vibrating? For example, we talk about an electric field. Well, what is that really? Is this some sort of, or a magnetic field? I mean, I can feel magnets pulling each other. But what about these so-called field lines that we learn about? When you draw these lines, which are supposed to be the magnetic field. Does that field really exist? Is there something really there? Or is it just a way to talk about the phenomena that you feel, which are magnets attracting? Similarly, same thing with gravitation. Newton himself was very dissatisfied. Very famous statement where he said it's kind of absurd to imagine a force of attraction operating without some kind of a medium. So, and then connected with that, the many attempts to think of it that there's an ether, there is some sort of a fine matter, which is the substrate of electrodynamics and of physics in general, an ether. Okay, well, but on the other hand, we know that in our universe, you have discrete objects, you have individuals. I call that individuation. We, people, individual organisms, are in a certain sense discrete. And we're in this universe, but we represent some objects of some sort. So there is individualization, individuation, sorry. We look up into the sky, we see all these objects, the stars, the galaxies, which are individuals. You have species of individuals in this universe, suggesting that it's not just simply some sort of lumps in an ether. So, okay, that's very interesting. And actually the debate about whether atoms and molecules really exist is, for example, water. Is it just a fluid, a continuum, or is it composed of molecules? This is a debate up into the 1890s. In a certain sense, the notion that these things really exist, they're not some atoms and molecules, electrons, really exist. They're not simply a convenient fiction. Took a very long time to establish itself. Einstein's work on Brownian motion, Avogadro, what's his name, Loschmidt, who arrived at an estimate of the so-called Loschmidt number, Avogadro number, that a gram of water has about 3,000 billions of water molecules. So it took a long time, and in a certain sense, this other current, you have the atomistic current and then the continuum current, So they were in a kind of conflict all the time. By conflict, I don't necessarily mean that they're mutually exclusive. That's where you get to the interesting problem. So then you have a turning point in 1900 with the I would say derivation by Planck, a theoretical derivation of a conclusion that action in the universe occurs in quanta, or in particular that the absorption of electromagnetic radiation by atoms occurs in certain portions of energy, which are apparently indivisible, quanta of action. And then going further, 1905, Einstein with his hypothesis that the emission of light takes the form of photons, what we now call photons, quanta of energy. Electromagnetic energy is transferred from one system to another, not in a continuous manner, not in arbitrary amounts for a given frequency, but in portions, whatever that means. So we now, I'm saying a lot, and there's an infinite amount of this written, and I'm being very sloppy just to remind you of these things. I'm not trying to be precise, but already Einstein, by latest Einstein, noticed a real paradox with this idea of light quanta. I mean, firstly, there was no provision for this in the classical electrodynamics of the notion of light as a continuous vibration of the electromagnetic field. There's no provision for that, so it created a dissonance that would have to be resolved. On the other hand, just in a very elementary way, let's take a point source of light, and let's say it's producing 1 billion photons per second. Now we go down to a nanosecond. And so in the average billionth of a second, there'll be 1 photon emitted. And what's going on in the remaining part of that interval, or in an interval of a trillionth of a second, which doesn't happen to have a photon? Nothing. There's no light. So that's also a little bit strange. Well, again, according to the electromagnetic theory, the intensity of light is continuously variable. It never gets to be 0. Another aspect, let's take our point source and let's surround it by a sphere. And now, according to the commonplace, according to experiment also, light is produced by this point source, and it spreads out evenly in spherical waves. The intensity is going to be the same at all the points on the surface of the sphere, the interior surface. But if we now turn down the intensity, or we take very small intervals of time, so that let's say we take an interval of time where there's only 1 photon produced, where is it going to land? Who decides at what point, or what determines at what point that photon lands? No provision. There's nothing in the physics up to that point, except maybe some kinds of intuition, nothing that even provides for that kind of question. So you get to this, the paradox becomes even larger with the so-called double slit experiment, which displays when you do it with modern technology. On the one side, if you do it with very intense light, which you can still think of as a continuous process, you get a diffraction pattern. You'll see it in a moment. If you turn down the intensity of light, then you get point-like impacts on a screen that only when you continue the experiment for a long time gives you this pattern. So we'll go through that. I'm going to show you a really nice part of a really nice video. And if you don't like the rest of my presentation, you can thank me for showing this one to you. From a Japanese company, I think is Hashimoto Photonics, is a great company that makes sensors and other devices for measurement of light at very low intensities, among other things. So this is a very nice video that shows you an experiment where the paradoxes, really some of the most important paradoxes associated with quantum physics, come up. So now I get to my PowerPoint and hope that you will be able to see it. Is it visible?
No.
No. Oh, share screen. Now I get it. Just a second. Share screen here. All right. All right. Okay. Let's see if my thing does actually. Yeah, there we are. Is this now visible?
Yep.
Yep.
Can you hear me also?
Yes.
Yep. Okay. So you're going to see now, here is the famous double slit experiment. You can do it with not just with light, but you can do it with electrons and other so-called particles. And here you see to the right, the screen at the back of the double slit experiment, where you see little dots, which are the impacts, which we interpret as the impacts of the particles, whether they be individual particles, photons, or electrons, which then accumulate, and when they get more and more of them, start to produce a pattern, which coincides essentially with the pattern you would get if it were a continuous wave, which is interfering with itself and producing that pattern. So here we go with the video.
To understand the wave properties of light, let's first look at the behavior of waves on the surface of water. We vibrate the water's surface so that we can see the shadows of the waves on the screen. There appears a pattern of light and dark lines. This fringe pattern is caused by the interference of two different waves. It is a property of all waves. If light has wave properties, we should be able to observe the same phenomenon. Let's run an experiment to find out. Here we use double slits to divide the light into two separate beams. Let's look at the behavior of the light after it passes through the slits. The same kind of fringe pattern appears as with the water waves. This pattern is caused by the interference between the two beams of light after they pass through the slits. The bright areas on the fringe pattern show where the two beams strengthen each other, while the dark areas show where they weaken each other. This clearly shows that light exhibits the properties of waves. Let's regard light as a kind of wave and compare it in a different way with another phenomenon that also has wave properties: sound. As you can see, when we decrease the strength of sound waves, their amplitude also decreases until they finally disappear. This is another property of waves. Does this same phenomenon occur with light? To find out, we'll try another experiment. In this experiment, we use neutral density filters to reduce the amount of light gradually. We then convert the light into an electrical signal, so we can observe on an oscilloscope how the light changes. we reduce the amount of light entering the filters. The number of signals, which indicates the strength of the light, has gradually decreased as well. Now we weaken the light even further. The overlapping signals separate and become more sporadic. Now we make the light still weaker. This light is too faint to be seen with the naked eye. The number of signals has decreased even more, but the strength of each signal does not drop below a certain point. This is clearly different from the phenomenon we observed with sound. The reason the signals do not decrease no matter how weak the light must be because light consists of some kind of minimal, non-divisible, particle-like units. In quantum mechanics, these units are called photons. So how can we explain the results of our earlier experiment that showed interference between waves? Does light lose its wave-like properties when its intensity decreases into the single photon region? To find out, let's observe the behavior of light in the region where individual photons can be observed. In this experiment, we use a photon-counting image acquisition system, or PIAS, that was developed by Hamamatsu Photonics to capture and analyze events at extremely low light levels. The PIAS makes it possible to detect and record the spatial location of photons one at a time. This illustration shows the operating principle of the PIAS. The system converts extremely weak light into electronic signals, which are then amplified and stored as spatial signals and displayed on a television monitor. The PIAS can detect and record light that has an intensity as low as 1/billionth of a lux. The light from a starry sky has a brightness of 1,000th of a lux, so 1/billionth of a lux is 1,000,000 times darker than that. Now let's start our experiment. Our light source is a low-pressure mercury lamp. We use ultraviolet light passed through a metal interference filter. The light has a wavelength of 253.7 nanometers. It passes through a single slit to increase coherence, and then goes through the double slits. We observe and record its behavior. Now we reduce the amount of light with neutral density filters. The photon count is 100 per second. At this intensity, no more than one photon at a time will be in the test device. This is the light intensity region where we make our measurements. The experiment has begun. The particles of light that have passed through the slits appear on the monitor as small points. 3 minutes later, the behavior of the particles seems completely random. The experiment continues. After 25 minutes, a pattern is emerging in the distribution of particles. 6 hours later, a fringe pattern has appeared. Let's compare this pattern with the fringe pattern we obtained in our earlier experiment. they're exactly the same. Although we thought of the photons as individual particles, they formed interference fringes. However, a single particle usually cannot create an interference effect. Is this true in the case of photons as well? Let's find out how the individual photons passed through the two slits. We'll try shutting one of the slits. The number of detected particles drops by half, and no interference fringes appear. This shows that each photon passes through both of the slits simultaneously and interferes with itself. While we have shown that light has particle-like properties, this experiment also shows that light behaves like waves when it passes through two slits at the same time. That means that light has the properties of both waves and particles.
Okay, so what do we do about this? I hope that you, in seeing this excellent presentation in the movie, get an idea about the paradox of this. You have these individual events, these photons that we interpret as particles, and there's some sort of an invisible hand, you might say, although on the short time period, it looks like it's just random distribution, but over a longer period, there's something operating which is producing these wave-like results. So now it's very interesting in, these are the Einstein and Planck that took some major steps toward the development, laying the basis for the quantum theory. And here are two of the founders and creators of quantum physics or quantum mechanics. The one to the left, Louis de Broglie, or de Broglie, I don't know how it's pronounced properly. I mean, in French it's de Broglie. In 1924, already in his doctoral thesis, put forward a very, very interesting idea, and which he called the onde de guidage, the guiding wave concept. And his notion was that what you have here is a combination of particles coupled to waves. There's a coupling in which the wave guides the motion of the particle. That's why the onde de guidance, or his pilot wave. And that was connected with his notion that the particle is not some kind of a dead, unchangeable object, but the particle has some kind of a process going on, which has a frequency, and he, through relativistic considerations, proposed what the so-called de Broglie frequency. It's depends on the velocity of the particle, its energy, and that this frequency is coupled with the frequency of the wave, so they're in phase. So you have both a particle and a wave, and the wave in this sort of is a way intuitively that the particle feels its environment, a sensorium of the particle, you might say, very intuitively. Unfortunately, when the quantum mechanics in this mathematical form, which is essentially continued until today, with some additions of quantum electrodynamics, basically it's the same. Quantum mechanics today is basically the same as it was after 1926, 1927. When Schrödinger and then Heisenberg at the same time, in a different way, codified the quantum mechanics, they did not take up this idea of de Broglie, but they went in different directions. Schrödinger was very much thought in the direction of continuity. His idea was basically that you really only have waves, and particles are sort of a foam or somehow constructed to build up out of the waves. And this is his so-called wave packet notion. The hypothesis that the particle is essentially produced by a superposition, by a combination of waves of different frequencies. That would be and where they come together, you have a concentration of energy. And his idea is that a particle was something like this. It didn't work out too well. It turned out that these wave packets would not stay together, at least not according to the equations he had, which are too linear, but would tend to spread apart so the particles would get smeared out and would not remain as particles. But in any case, that was his approach. He also later, in one paper, for example, attacked the idea that there could be quantum jumps, and put out an alternative view of this, where you have a continuous back and forth transfer of energy between two systems, but not a jump. And on the other hand, you had Heisenberg and Niels Bohr. Oh, I should say, the Schrödinger approach gave a very, very nice and very beautiful and very useful interpretation of the energy states of atoms as eigenstates, or what you might call as analogous to what was already known for a long time in acoustics as the Chladni figures. If you take a metal plate, and you vibrated it at certain frequencies, and here sand is put on the plate, then at certain frequencies you get a resonant mode of vibration, and they form the beautiful patterns called Chladni figures on the plate. And that occurs only for certain discrete frequencies, which in the case of transferring that to the Schrödinger quantum physics, which he called wave mechanics, correspond to the energy states of an atom. So this worked out very well and is still used today, although the wave function is not interpreted, so to speak, as something actually being vibrated. This is a problem. What is the wave function of Schrödinger really? Then you had the other direction, which was particularly Heisenberg here in the middle, where he developed something called matrix mechanics, which you can already tell from the name is very different. It's not it doesn't give an intuitive picture like a wave, but it's a mathematical formalism, purely abstract, in which the states of a system correspond to vectors in an infinite dimensional space, and parameters such as momentum or energy are mathematical operators, infinite dimensional matrices, which operate on these vectors. So you're very, very far away from any kind of a understanding in the usual notion of what's going on here. But, and students generally have to learn both of these directions. The Heisenberg approach is really very dangerous to one's mental health if you try to, try to apply intuition to it. Therefore, students are told essentially, shut up and calculate. The important thing is get the right answer. Don't try to understand it. But in fact, the view associated with this, which Niels Bohr particularly articulated, was the idea that as I already mentioned, that there is no possibility of understanding, you're at the limit. And also, even the notion of an objective reality that you're describing or trying to get at is, let's say, flawed or irrelevant in a certain sense. I won't go into this in detail, but just a quote. This is a quote from Niels Bohr. about the wave-particle aspect. We're not talking about contradictory, but complementary pictures. There are different attempts to interpret the evidence. We can no longer speak of the behavior of the particle independently of the process of observation. So it's not an objective processes, but you have to include the measurement. But when you include the measurement into what you're observing, then you've got something different than the object you're trying to observe. You have an interaction. Impossibility of any sharp distinction between behavior of atomic objects and the interaction with the measuring instruments. I just give an example. Now here, Albert Einstein, as I mentioned, was one of the people objecting to this, calling this a tranquilizing philosophy, which provides a pillow for people who don't want to go further, essentially. And Schrödinger, even more, Bohr's approach to atomic problems is really remarkable. He is convinced that understanding in the ordinary sense of the word is impossible. And he attacked Bohr by saying, aren't you afraid that what you're saying about the incomprehensibility is going to turn out to be ridiculous, and you're going to turn out to be a fool in the eyes of history? There he's referring also to another aspect of the so-called Copenhagen interpretation of quantum physics, the notion that this randomness or partial randomness that we saw in the experiment with the photons is intrinsic. That is, that it is impossible to predict exactly where a photon will land. And the Schrödinger wave function is not objectively real. It's only a way to describe the probability. It gives only a probability for finding the particle in a certain place at a certain time. So Schrödinger rejected that and said, look, it's just because we haven't gotten further. Einstein also, the fact that you say this is only random means you don't understand something, and you have only a partial theory. So now this notion, what came out of this mathematical formalism, the Heisenberg formalism, but also the Schrödinger wave, which Schrödinger hoped would be a real physical wave, but is then now regarded as a probability wave, as a mathematical fiction, which allows you to predict probabilities. Out of this and other paradoxes of quantum mechanics, and particularly the way it's taught, came the general consensus that don't try to understand it. As I say, shut up and calculate. And here we have one of the great superstars of modern physics, Richard Feynman, saying here, I think I can safely say that nobody understands quantum mechanics. And when he's talking about the double slit experiment, nobody can give you a deeper explanation of this phenomenon than I have given. So there was a real acceptance, even of the most brilliant physicists, that this was really the last word, and that you won't get any further. Well, this was not, as I mentioned, there's a dissident faction. One of them was David Bohm, you see to the left, and John Bell. Can't go into details because of time, but David Bohm, in 1956, I believe, developed a mathematical formulation of the quantum physics, which is equivalent, gives exactly the same predictions as the Heisenberg-Schrödinger forms, but has a particle and a wave. And the wave and the particle interact in such a way that as to produce, for example, the interference patterns which we saw in the experiment. Now, how is that possible? Well, that can only be possible if the particles have rather complicated trajectories, and in fact they do. Now this is according to the mathematical equations of Bohm, which may or may not be correspond to reality, but they give you this sort of pattern. Now here you see to the left, you have to imagine the wave coming in. These lines represent the trajectories of the particles, and you see that they are bent. So you have to imagine you have the wave, you have the particles coming in, and both, and in Bohm's interpretation, the particles a given particle only goes through one of the slits. It's a real particle. It doesn't do what the movie said, through both. A particle goes through only one slit, but the wave goes through both slits. And the wave affects the trajectory of a particle after it has gone through a slit in such a way that if you see on the right side, you end up with a pattern corresponding to the diffraction pattern as a result of this interaction between the wave and the particle. So by this, Bohm did not claim that this is exactly the way things are, but he said, look, this means that we don't have to have this abracadabra. There's no reason to reject the notion that there is particle and a wave. No, because here's a formulation that gives you exactly the same predictions. And more recently, there's been an attempt to observe in a certain sense, this is very indirect observation, actual trajectories of particles in this sort of experiment. This is controversial because you're detecting the particles using coupled pairs, entangled, so-called particles, where you measure where one particle goes through the experiment, the other particle separate, and you use it to gain information about what the trajectory of the first particle. Anyway, it's somewhat controversial, but at least gives you a certain kind of indication. Maybe this is really what's going on. So now I want to go to a big surprise, which I think nobody expected. Do I have 15 minutes, Matt?
You have as much time as you want, Jonathan.
Well, okay. Well, we'll see. Well, I want to get to the end so we can have a discussion. But let's see now. In the 90s, a very unexpected event occurred. People like me and others had the conviction that part of the problem here is that the phenomena are nonlinear, that the mathematics of the models were far too primitive, and that there's a so-called nonlinear phenomena going on, and that was the direction to look. And part of the problem was that at the time that Schrödinger tried to make his wave packets to have the idea that somehow there's a coherence between the particle and the whatever wave or some kind of spatially extended process. At that time, nonlinear processes they're hopelessly difficult to solve explicitly mathematically. But in the meantime, there's been tremendous progress in mathematical modeling, in doing experiments where you could simulate various nonlinear processes. I mean, the wind tunnels were one way, which is still used today, since you can't calculate the so-called Navier-Stokes equations solutions explicitly, except in exceptional cases. You do simulations. In any case, what I wanted to say is there's been advances where now you can actually test hypotheses out that was not possible before. Guesses, feeling around, and maybe there's some kind of nonlinear way in which particle-like entities are generated in a process. In any case, in the 1990s, a very unexpected event occurs, which is presented in the next video. which you'll find quite entertaining. A French physicist named Couder discovered a phenomenon actually in hydrodynamics, which completely unexpectedly displayed characteristics of these wave-particle dualism and opened up the possibility of a kind of way of thinking, of a model for these processes. So let's look at not just a theoretical thing like the Bohm formulation, but something was actually a physical process. So here we go.
For most of the 20th century, scientists believed quantum physics could not be explained, that we would just have to accept that we'll never know why things behave as they do down at the deepest levels of existence. But now, a growing band of rebel scientists thinks there may be a logical explanation for quantum weirdness after all, and new hope for revealing the ultimate truth of our universe.
The trail begins here, with a drop of silicon. In his Paris laboratory, physicist Yves Couder and his team conduct an amazing series of experiments. They are observing the behavior of silicon droplets bouncing in lockstep on a vibrating plate.
The liquid of the drop never touches the liquid of the substrate, so they're always separated by air film. And in fact, this is stable. You can keep the drop bouncing on the liquid surface for several days if you wish.
Using a camera that shoots 1,000 frames per second, Couder has discovered that these droplets mimic behavior seen in the quantum world. And that shouldn't be possible, because the quantum world and the large-scale world play by two different sets of rules. Yet here we see a single droplet moving randomly like a quantum particle, but behaving like a quantum wave. If you watch this carefully, you'll notice that the wave appears to be guiding the droplet. In fact, the wave fields around the droplets develop a memory of the trails they have followed. Despite their random behavior, they follow a small number of paths. Again, this is eerily similar to the behavior of quantum objects. This runs so contrary to popular belief that at first, Couder refused to believe what he was seeing.
In any physics experiments, you only see what you are prepared to see. Of course, this was very obvious that there was a memory, but it took us some time to realize that it was that we were observing, because you have to adapt to this new idea.
Perhaps most revealing of all, Couder has reproduced the double-slit experiment using his bouncing silicon droplets. The mystery of quantum mechanics is, how can things like electrons sometimes behave like particles and sometimes behave like waves? Perhaps this is the answer. They are particles and waves. Of course, this system, though small, is not quantum.
Our system is not a model of quantum mechanics, but it is an association of a particle and a wave, and some of its properties are similar to the properties that are observed in quantum mechanics.
Couder won't claim that his experiments show us what is really happening down at the deepest layers of existence.
Yeah. Well, most of the... Okay, I want to stop it there and show you one more video done by, I think it's actually at Couder's lab, just to give you the idea about this randomness which was mentioned. Now, it was claimed, as I mentioned, the so-called Born interpretation, and Niels Bohr and so forth, that there's an intrinsic randomness of in the sense that you can't understand anything more about it. It's not like throwing dice where you can say, well, the die is rotating around in the air and lands, happens to land on one face. There you have a causal process which you can follow in time that gives a certain result. It has a random distribution, but the individual process can be followed. It's not something that has no reason to it. So, and the claim of Bohr and others was that that's different in quantum mechanics. You don't get to another level where you can see the causality which is leading to the individual events and leading to a situation where those events may or may not have a random distribution. Randomness essentially is ignorance about the detailed causes. At least that's the way we normally think of it. But here's the claim that in quantum mechanics that you have intrinsic randomness, which is not a matter of ignorance about causes, but is a property somehow of the world. So here we have a simulation. Here we have an actual experiment where you can see here the tray of the oil. It's being shaken from below here by about 70 hertz. And that causes a vibration of the surface and causes the drops to bounce up and down. When they bounce up and down, they create a wave pattern. The waves spread out into the whole domain in which the particle finds itself, and in a sense create a kind of memory because the waves are reflected by the walls, come back, affect the motion of the particle or the motion of the droplet, right? So you have a feedback process. The droplet is in one place, but the wave is all over. So it follows this this way of thinking of Du Bois. So here we go. Now what you're going to see is an apparently random behavior generated by this process, which though as you accumulate more and more cycles, gives us a pattern. So there's the droplet. This is a strobe picture where you only see, and there we are. We're tracking the droplet. It's wandering around. Here we're not seeing the waves, just the track of the particle. And now, and keeps going, keeps going. Now we're beginning to see that it's in some areas more dense than others. Does that remind you of the other video we saw with the photons? There we are. And so you get a wave pattern, which is actually corresponds to the so-called Faraday waves, which are the waves you get if you vibrate the surface at very high amplitude. This would be, so to speak, the Schrödinger wave or De Broglie wave and distribution, but it's the product of a dynamic process. So, okay, I want to close. So this is very exciting, and it's shaken things up. And in July, I participated in a conference about these kinds of models of quantum behavior. There's a fellow named John Bush, who is, I think, in Texas, who has a whole institute devoted to this kind of CUDA processes, which he calls hydrodynamic models of quantum physics. The conference was called Advances in Pilot Wave Theory. And now I gave a presentation on something that seems to be quite different called the Dubushinsky pendulum. This is how I got into this whole field. I had gotten to know a Russian physicist named Dubushinsky, Daniil, at a conference, who, together with his brother in the 1960s in the Soviet Union, invented or discovered a phenomenon of which he called macroscopic quantization. Now here we're getting to a bit of a different aspect of the quantum physics, namely, why or how are the energy states of atoms quantized? In other words, why do we have a discrete set of spectral lines, which is usually interpreted by the idea that atoms can exist in only a discrete series of energy levels, and when an atom falls from one level to another, it emits light, and so you get a discrete number of possible frequencies or energies or frequencies produced by an atom. Yeah, I'm talking about energy levels of an electron in an atom, orbits, we'd say. The orbits are quantized as only a discrete set of them. Well, Duboshinsky discovered a system which is you would call a classical system, which you can build, very simple, which displays this kind of behavior. And we'll see it. I'll show you a movie also. I just show you a couple of slides from my presentation. I started by quoting De Broglie, and actually this is relevant. De Broglie later went a step further than his pilot wave consideration, namely the idea that there's a background process we might call a subquantum medium, which the particle is interacting with, and the wave, and to a certain extent the metabolism of the particle, are to be understood as a dynamic process of interaction, so that there is a subquantum level, and quantum physics has, the existing quantum physics has not yet gotten at that subquantum level. In fact, in the 1926 Bohr Heisenberg quantum physics actually denies that this is even possible. So this is very revolutionary, although De Broglie already had this idea. He called it a thermostat, which I don't know why he used that word. In any case, here is the quantization of energy levels in the hydrogen atom. And we want to understand why there are these discrete sets of orbits, of electron orbits, possible electron orbits in a hydrogen atom. So one approach to this is that we now have lots of examples in physics of nonlinear processes, macroscopic, where there's no abracadabra, systems that can exist in a discrete set of different stable configurations, stable states. Well, this is actually nothing new. If you take a chair, for example, a chair basically has two stable states, one sitting the way it should and the other tipped over, or maybe there are four, depending on which side it gets tipped over on. So there are, let's say, 5 stable states. So we could say that the chair is quantized, right? I mean, from that standpoint, the question really is, I won't go into the details of the study of these so-called multi-stable systems. You have lots of them, and it's a big field of physics now, with a lot of applications to engineering. If you build a rocket, for example, or a bridge, you really want to know what the different states are going to be. You want to be in a stable state. You don't want to have some other possible states near it. In any case, if we want to get to this deeper level, it's not enough to just say, okay, well, we have physical processes, physical systems which can exist in a discrete set of stable states called attractors in modern nonlinear dynamics. But we want to find some kind of a paradigm, some kind of the simplest possible way that such states could be generated as a point of departure, possibly, for thinking about how this kind of thing comes up in a very universal way in quantum physics. So here we have Daniel with his pendulum to the left. What is the pendulum? The pendulum has a pivot up here.
I'm sorry, Jonathan.
Yeah.
The previous slide you were just showing, what were those two images we were looking at? The basin. Could you describe that?
Well, very, very simply, you have something called the sort of phase portrait. You take a system here, you have a system, it's an oscillator with one variable, something that can move in one dimension. I'm talking about the left-hand side. And now you look at the pathways. When it moves, its position, that's the x-axis, and its speed, its velocity, are, so to speak, two coordinates. If you follow that in time, like we were watching the droplet moving in a certain way, right? It will follow a trajectory. And those trajectories you can plot will move in certain regions. And in certain regions, there'll be so-called attractors. In other words, if a trajectory gets in there, it will stay. So these dots here are areas of stability.
Is that sort of like a Lagrange point? Or something?
Yeah, roughly. You might. We are sort of, sort of. It's not a complicated thing. You can easily, sort of a standard thing. You have phase portraits. You have any kind of a process. It develops in time. You have certain parameters, variables. They move with time. You plot that. If there are two variables, you can plot it. The trajectory, the development of the system, the evolution of the system as a curve in a plane. And now you can look at how all those trajectories are distributed, and you will often have so-called attractors. In other words, a trajectory will start somewhere, and it will end up cycling into a certain area. For example, the Rayleigh-Paoli dowel, the one that what do you call it? You tip it over, but it tips back up. That's what you would call an attractor. In other words, a state where if you start somewhere, you generally end up in a certain region. And this is a way to graphically study and represent these kinds of so-called multi-stable, where there's not just one, but several areas where trajectories will end up, depending on where they start, right? And this is a big deal. You can use it in psychology. It's used today in all kinds of areas, right? Somebody goes to school, will follow a trajectory. Maybe they'll pass. Maybe they'll fail. Anyway, I don't go. It's nothing deep. Just sort of a way to picture processes. So here we have the De-Mystified pendulum. It's just a pivot pendulum here, normal pendulum. At the end of the pendulum, we mount a magnet. Yeah. And here, under the vertical position of the pendulum, we have an electromagnet, which is supplied with an alternating current of some frequency. It can be it's convenient to use 50 hertz, but you can use 1,000 hertz if you have a current source. And now when the pendulum is outside, is not as far enough away from the electromagnet, the magnet at the end of the pendulum doesn't feel any force. But when it gets near to the electromagnet, it will be accelerated, attracted, or accelerated, or decelerated, depending on in which direction the current is flowing at that moment in the electromagnet. So it's an interaction of two oscillating processes. A typical pendulum might have one oscillation per second, and it's interacting with the system with a frequency 50. And there is Daniel, and this system displays a discrete set of stable states of motion, stable amplitudes. Now we know an ordinary pendulum, if you drop it from a certain height, it will continuously lose energy because of friction until it stops moving. In this case, however, the pendulum is so clever that it can pick up a little bit of energy in crossing the magnetic field at the right time and get enough energy to compensate for its losses. That, however, involves a coordination between the phase of the electromagnet and the moment at which the pendulum enters into the interaction zone, we call it. So here we'll see, I'm sorry, the quality may not be the best, but you get an idea. This pendulum is now quite famous. You can, I presented it at a lot of conferences and wrote about it. It's now also a kind of a favorite laboratory experiment for high schools in Russia. And you can find it in Wikipedia and so on. So here we go. He's going to release the pendulum. There you see the electromagnet here below. And you see it in its, so to speak, lowest energy state. It maintains, and now he puts it in a higher energy state. So, and you see it, of course, you can't wait for minutes and minutes, but it will keep at that amplitude without losing height for hours. Here you see this point where it's crossing the electromagnet. And that's the key moment where it can pick up or lose energy. Here you have, if you look carefully, here is at a very high amplitude, and you'll see that it runs into a bad phase and loses energy. The amplitude is not constant. Oh, it hit a bad phase. Oh, it's collapsing. This is a physics class in Russia.
Потери энергии на трение никуда не исчезнут, но теперь они будут компенсироваться за счет Мы видим, что с амплитудой 30 градусов маятник совершает одно колебание за 20 периодов переменного тока.
So different amplitudes, you get different frequencies. And now here's the zoo of Duboshinsky, where you can have as many little pendulums as you want that are all feeding on the same source. Each has its own frequency and can sustain itself, each one in a discrete set of stable amplitudes. So it's really neat, and it's has a lot of interesting characteristics because apart from the quantization, from the existence of a discrete set of amplitudes at which the pendulum can sustain itself. In between them, if you start the pendulum at a certain height, it will either go into one of these stable modes, or it will finally collapse down to the vertical position. So you have a lot of very interesting phenomena. Let me just see here. This is just my presentation at the conference. I don't think I have anything here more than I wanted. There's a mathematical kind of a theory of how this happens, but it's not, well, I don't want to go into details. This is here, right? You see one of these typical trajectories. These stable states are what you call attractors, where the system evolves toward a more or less stable repeating process. Yeah, it's just the analysis. These are simulations. Yeah, this is by a paper in China by a Chinese group, where it's interesting that the amplitude of the pendulum is never constant, even in one of these stable states. It's always fluctuating, and this is for Daniel, for Duboshinsky, and also for me, a key thing. This constant fluctuation is, according to him, and I believe it's correct, is actually the mechanism of stability. It's through these small variations that the system is able to keep itself in the stable range. At the right, you have a simulation where it starts with the same amplitude, but the wrong phase and it gets damped out. Here you see also this oscillation. This is an actual measurement. Anyway, this is one of these phase portraits, as they're called, with the attractor range, which again would be too lengthy to go into. I want to now conclude. Yeah, just a couple of remarks about the work that I've done with Lubushinsky. One crucial aspect, you see the title there of a paper. This is independent of Kuder, but the same kind of an idea to find a bridge of intelligibility between these quantum phenomena and phenomena that you can follow that are intelligible in macroscopic systems that don't have some kind of abracadabra, right? And open up, let's say, open up your mind to possibilities for understanding the quantum phenomena, which we can't see directly, on the basis of ideas and inspiration taken from these systems. But one very important point, you see here a paper of ours called The Universe as a Social Process. And there you have an idea which I can only mention here, and an idea of a physical object, where we get to De Broglie's notion of the subquantum and so on. Look at a physical object as a dynamic, always dynamic. There is no such thing, or in this way of thinking, as a static entity. All entities are support themselves by some kind of action. And the interaction of two of these so-called objects is itself an object. You have actually as you say, A plus B doesn't just give you C, but A plus B gives you a whole range of objects. In this case of the pendulum, these objects are the stable states of interaction of the pendulum with the electromagnet. So, to make a long story short, this is not my subject here. We're trying to feel our way toward a situation where one can come up with hypotheses, and in parallel with new experiments, because now people can begin again to do experiments which earlier would be dismissed as, yeah, why are you doing that? We already know what the answer is, right? So the door, although this is not some kind of new quantum physics, right? It opens the door to thinking in a fresh way. So that at least is for me, a very optimistic a reason for optimism, that we will have a further revolution, or at least in this area. Anyway, thanks a lot for your patience, and I hope you have some questions and comments. Thanks a lot.
Thank you, Jonathan. Thank you so much. And I just have to, well, there's so many things I want to say, but if you could send me these papers, and I could include them in the description, so people who want to dig in more deeply into your work with Dr. Lubushinsky, they would be able to do it that way after being inspired by this video. The first thought that I noticed that came through the pipeline was from Fletcher James. So Fletcher,
hi Fletcher.
Why don't you take yourself off mute, Fletcher, and you could pose your thought.